Now, define an important quantity in this regard, which is called as a latent heat, which is what is written here. So, we will erase this part, and this latent heat can be now discussed. It is also true that the amount of heat required depends on the nature of the substance or the type of material that you are putting or you are considering. Okay, so, the definition of latent heat is it is the heat per kg that must be added or removed when a substance undergoes a phase change or change in phase from one to another. Okay. And this latent heat is accompanied no change in temperature, as we have seen. So, is a per kg is a heat required per kg of the substance, which is undergoing a phase change from one phase to another phase, and as we have seen that it is accompanied by no change in temperature. So, there are three kinds of latent heat which we can define. One is called as the latent heat of melting. So, we will talk about three kinds of latent heat. For that, let us remove this part for now. So, the three kinds of latent heat. One, we will call it as Lm, which is latent heat of melting, but as I said that it is also called as latent heat of fusion. So, this is latent heat of melting or fusion. Which is associated with a melting of ice to water, and number 2 is LV. So, it is a latent heat of vaporization. So, latent heat of vaporization, and number 3, it is latent heat of sublimation. Okay. So, and the SI unit of latent heat is SI unit is joule per kg. Okay. So, this is by and large the definition and kind of latent heat. So, let us see some representative values for some known substances. Let us just talk about liquids for now. You will get data for solids also. So, let us talk about the latent heat of melting and the latent heat of vaporization for some of the known liquids. So, we have material, and let us call is the melting point, and let us call it T m, and it is expressed in, say, degree centigrade. Now, it is L m, which is latent heat of melting in joule per kg, and let us call also let us also record the boiling point. I am simply writing it as P t as point, just to save some space here, and this is again in degree centigrade, and let us call it by T b, and now L v again in joule per kg. So, these are the parameters that we are using, and let us write as ammonia, whose melting point is minus 77.8 degree centigrade. The value of L m, that is the latent heat of melting or fusion, is 33.2 into 10 to the power 4. Its boiling point is 33.4, and it's 13.7 into 10 to the power 5. That is for ammonia, which is known as so your NH3, and now it is benzene, and this is 5.5 is the melting point. This is 12.6 into 10 to the power 4. This is 80.1 degree centigrade, and it's 3.94 into 10 to the power 5. So, this is for benzene, and for mercury, this is minus 38.9, and it's 1.14 into 10 to the power 4, while mercury has a very large boiling point, which is 356.6 degree centigrade, and it's 2.96 into 10 to the power 5, and water, this has a melting point as 0.0, and which is equal to a 33.5 into 10 to the power 4, and this is 100 degree centigrade, and this is a 222.6 into 10 to the power 5. One interesting thing that you can note here is that the order of magnitude for L m and L v for all these 4 liquids that we have considered are same, that is all are L m, which is latent heat of melting, is of the order of 10 to the power 4, and this is 10 to the power 5. So, this is between 10 to the power 4 and 10 to the power 5, and this is between 10 to the power 5 and 10 to the power 6. While the melting point and the boiling points are very different, such as the melting point of ammonia is minus 77.8 Kelvin, 8 degree centigrade, whereas it is 33.4 degree centigrade, and so on. And for mercury, the boiling point is very high, and the melting point is below the freezing point of water. But however, the LV and LM have somewhat similar in dimensions or in the order of magnitude. Now, let me give you an example of the sublimation. So, where a system directly gets converted from a solid phase to a gaseous phase. Now, this is it is this is one of the applications of color printer. You have seen color printer, which has become very popular in office use and also sometimes in home use. So, what happens is that there are mainly 3 colors that are there. So, I am giving you an example of sublimation. So, we consider this color printers. The color printers primarily uses 3 colors, which are cyan, which is blue, and yellow, and magenta. So, they are kept in 3 different containers there, and the printer head, which is connected with a heating filament, transports this colors in 3 steps, one for each of the color, from the container to the paper. So, this printer head has a heating element, which directly converts the pigments, which is the colors, in solid form to a gaseous form, and there is a coating on the paper which absorbs this and makes a mark. So, all other colors that you see in a color printout are combinations of these colors. So, the sublimation occurs when the printer head, which has a heating filament, directly converts the dye or the color in solid form to a gaseous form, which is later absorbed by the material of the paper and printing is done. So, now we move on and talk about another interesting part of the thermal properties of matter, which we call as heat transfer. So, transfer of heat from one body to another body, or transfer of heat from one body to its surrounding is what we are going to talk about when we take up this heat transfer for discussion. So, now we will talk about heat transfer, and this heat transfer is an interesting component, or rather a subject in this thermal properties of matter. And the transfer of heat takes place mainly in 3 ways. One is called as a convection, 2 is called as the conduction, and 3 is called as the radiation. And so what is, let us start with this first one called as convection. So, you must have seen that fire is lighting, and the fluid or the air around it, what happens to it is that it gets heated up, and hot air expands, and because it expands, the density goes down and it becomes lighter. So, lighter air just resides in the vicinity of fire. Now, Bernoulli's principle says that this should rise, and the neighboring cooler air, which is more dense, should rush in to fill the void. And now they come in contact with the fire and becomes warm, expands, becomes lighter, move up, and more air will come in. And that is the way there is a heat current that is set up, and this heat current is called as a convection current, and this process is called as convection. Okay. So, a heat current is established which is known as convection current. You must have seen that in television that there are fire in buildings, and there is black smoke that comes out and it rises into the air, and it rises into the air because of this convection current, or because of this process of convection. And there are a number of interesting different phenomena that occurs due to the convective current of air that is around us. So, let us look at the second one, or the second mode of heat transfer, which is called as the conduction. And so, this conduction is a process whereby heat is transferred directly through a material. And so, is basically the transfer of heat from one material to another mediated by another material medium, and this can be sort of understood in this particular fashion when you have two bars which are kept and they are connected by and there is a area of cross section that is there. So, there are two bodies which are kept at different temperature. Let us call them as this one as hot at a temperature T1, this one is cold at a temperature T2, such that your T1 is greater than T2, and it is connected by a material medium which has a cross sectional area, let us call it as A. So, A is the cross sectional area. So, the heat that flows from the hot body to the cold body, so heat Q is proportional to the area of cross section, it is proportional to the temperature difference between the cross section between the two ends of the rod, and it is also proportional to the time for which the process takes place, that is they are allowed to be in touch, and it is inversely proportional to the length of the connecting medium. And if we put everything together, so it becomes equal to Q is A delta T T by L, and we have to put a proportionality constant which is put by a capital K, and K is known as thermal conductivity. So, K is called as the thermal conductivity of the medium, and it is expressed in joule per meter per second degree centigrade or Kelvin, depending on how you are expressing it there. Now, let us try to do some problems here in order to gain more understanding on this thing. We have a problem which is from the book, and this problem is stated as the following. So, an iron bar, this is a problem on thermal conductivity, and we are stating the problem to begin with. An iron bar which is 0.1 meter long, area is 0.02 meters square, and also the thermal conductivity, we are all expressing it in terms of 1 for the iron. So, K1 is equal to 79. Now, this is given in watt per meter per Kelvin, and a brass bar with the specifications as again as 1 meter and same area of cross section, but with different thermal conductivity, because we know that the thermal conductivity depends on the material. 109 watt per meter inverse per Kelvin are soldered end to end. Soldered means they are joined end to end, and so this is the figure for that. So, this is iron and this is brass. This is kept at a temperature which is higher, let us call it as temperature T1, and this is kept at a temperature T2, which is written here. The free ends of the iron bar and the brass bar are kept at the free ends of the iron bar and the brass bar are kept at T1 equal to 373 Kelvin and T2 equal to 273 Kelvin respectively. So, now the question is twofold. One is that obtain the temperature at the junction, that is at this point. Let us call this point as O. Obtain the temperature of the junction. let us call it as TO. Second part is that the equivalent thermal conductivity of the compound bar. And the third question is the heat current so obtain the equivalent thermal conductivity and obtain the heat current. So let us put this obtain here. The heat current through the so the question is simple, that we are talking about thermal conductivities of material. So we have an iron bar here whose free end is kept at a temperature 373 Kelvin, which is at T1, is soldered with a brass bar, which the free end of which, the right side of which is kept at a temperature T2, which is 273 Kelvin. The question is, what is the temperature at the junction? Second question is that if I call this as one bar without really talking it as two bars, if it is a compound bar, what is the thermal conductivity of the compound bar? And the third question is that what is the heat current that flows through the compound bar? One understanding or assumption is that there is no heat loss otherwise. So, thermal conductivity, whatever heat gets conducted from one end, that is the left end of the iron bar, will actually flow through the heat current, same heat current will flow through the brass bar. Okay, so this is the question, and the question is easy to solve, just that we have to erase some part of the board in order to do this problem. Let us try to do it as much as we can without doing that. So, so we understand that there is a steady condition that is achieved, that is heat will start flowing from the hot end to the cold end, and the passage of heat will continue until a temperature equilibrium is established in the whole material. And so, under that steady condition, that heat that flows through the iron bar is equal to the heat that flows through the passes through the brass bar. So, this is given by H1, which is equal to K1 A1 T1 minus T0, that is the temperature difference. So, this is at T1 and this junction is at T0, and this is L1, and this is equal to a K2 A2 and T0 minus T2 divided by L2. Now, if you have a look at it, L1 and L2 are same. Here both are equal to 0.1 meter, and similarly A1 and A2 are same, which are both to be 0.02 meter square. So, we land up with so A1 equal to A2 and L1 equal to L2. So, we land up with a simple equation which is K1. So, this is equal to my H2. So, H1 is the heat that passes from the iron rod, and this is the that passes through the brass rod. So, at thermal equilibrium they are same. So, I get an equation which is K1 T1 minus T0 equal to a K2 T0 minus T2. One can easily solve this to get T0 or a TO, it is at the junction. So, TO equal to K1 T1 plus a K2 T2 divided by a K1 plus a K2. So, this is my temperature that at equilibrium will exist at the junction. Now, since we have looked at the question, one can erase the question for now, and all the data are of course can be written here. Okay. So, we have so if you take it as a compound bar, then my H, which is equal to H1 equal to H2, which is equal to my K1 A T1 minus T0 divided by L equal to a K2 A T0 minus T2 divided by L. And so, this is my the heat flow. Now, I can put in the T0 that I have obtained in part 1, that is this thing, and I will get a H, which upon simplification will look like a T1 minus T2 divided by L and 1 by K1 plus 1 by K2. So, that is the heat flow, and so this can be understood that if I now take this rod as a compound bar and write this formula simply as some K prime and a T1 minus T2 divided by L, this is of course the heat flow per unit time. The time has not entered into this consideration. So, your K prime will now be written as, if you compare between the two, K prime is written as twice of K1 K2 divided by K1 plus K2. So, that is the effective or the equivalent conductivity that exists for the compound bar. Okay. Now, the third question, the heat current has to be computed through the compound bar. So, the heat current can be computed as the following. So, the heat current through the compound bar is a K prime A and a T1 minus T2 divided by a 2L, and so this is so now we can put the value of K prime from part 2 and get the effective conductivity or effective heat current for the compound bar, which is now T1 minus T2 divided by twice L. So, that is the answer to the third part. So, this is the heat conductivity calculation for a compound bar. So, let us look at the third mode of heat transfer, which is called as a radiation. So, radiation is a process in which energy is transferred by means of electromagnetic waves. Now, the good thing about electromagnetic waves is that it does not require a material medium to propagate. So, since it does not require a material medium, radiation does not require a material medium for the heat to flow. And and also that the radiation occurs very quickly with the speed of light, and we know that speed of light is very large, which is 3 into 10 to the power 8 meter per second. That is the speed of light. So, the radiation occurs at a very fast rate, and so basically this is how the sun rays that come to the earth, which most of which between the space between the sun and the earth there is no material medium, and radiation emitted by a body by virtue of its temperature is called as a thermal radiation. And these thermal radiation, when it falls on another body, it either is perfectly absorbed, or it could be partially absorbed and partially reflected, or it could be all reflected. And this particular fact has an implications or an understanding on the kind of or the color of the clothes that we wear in summer and winter. In summer, one would like to wear a light colored dress because you want the light colored dress which absorbs very little thermal radiation or heat, and it reflects most of it, while in winter we would like to wear dark colored clothes which absorbs a lot of thermal radiation and reflects very little. In fact, this is also the reason that the bottom of the vessels are painted black in order for the heat to be heated very quickly. So, these are some of the interesting examples of radiation, and there is one particular formula that I would like to mention here, which is called as the StefanBoltzmann law of radiation. And what it says is that the radiant energy or radiant energy, which is the thermal radiation Q emitted in a time t by an object that has a temperature that has an absolute temperature T, a surface area A, and an emissivity, which is the emission power, and an emissivity small e. So, this is given by Q equal to E sigma T to the power 4 A and T, and this sigma is known as StefanBoltzmann constant, and this has a value which is 5.67 into 10 to the power minus 8 joule per second per meter square Kelvin to the power 4, and this is often quoted as a 2 to the power 4 law, where the radiant energy or the thermal energy due to radiation is proportional to the fourth power of the temperature expressed in absolute scale. So, if we know the emissivity of a certain body, you will probably hear about black bodies. Sun is a perfectly black body. Black bodies are will be taught to you, and you know the emissivity, etc. The sigma is the StefanBoltzmann constant, T is the temperature in absolute scale, is the area of that which is exposed to the radiation, and T is the time for which is exposed to radiation, is given by this formula, and it's called as the StefanBoltzmann formula. The next thing that we want to do is called as so Newton's law of cooling. So, suppose we have taken a liquid in a container, and say it is a thermos with which has a temperature or a thermometer that is inserted into the liquid, and the liquid is at a certain temperature, say at room temperature. We have inserted the liquid into the container, inserted a thermometer so as to note down the reading. And now what we do is that we raise the temperature of the liquid by adding heat, such that the temperature is raised beyond the room temperature. Say the room temperature is 27 degrees centigrade, and this container is taken, in which we have this is the liquid that is there. There is a thermometer which is kept with two. So, this is a thermometer, and there is also, say, a place for a stirrer to stir it gently. So, you want to stir the liquid gently, and it is initially at 27 degrees centigrade. Now, it is put under flame, and say the temperature of that goes up to 40 degrees centigrade. And you can consider the this container to be a thermos with a two-hole lid. There are two holes on the lid. One is to insert the thermometer, the other is to insert the stirrer. And now, what you can do is that you can now you remove the flame, that is, heat is no longer given after the temperature has attained 40 degrees centigrade, and you want to record the temperature after a fixed interval of time. So, you can record the temperature after, say, 5 minutes of time, or 10 minutes or 15 minutes, depending upon what you are interested in. And what you want to know is that how the temperature is going down with time. So, let us talk about delta T, which is the difference in temperature. So, you measure it at T equal to 0, and then at 5 minutes, at 10 minutes, at 15 minutes, and so on. And the temperatures that are found to be, say, T0, T1, T2, T3, and so on. And you want to note down a delta T, which is equal to a T0, T1 minus T0, or T0 minus T1, T0 minus T1, say, to because you have heated up the substance. and this is T1 minus T2. So, this is delta T1, this is delta T2 and so on. So, you want to record this delta T or the change in temperature with time. And what one finds is that one finds a curve like that. So, there are these data points that you get which fall on these this line, and say this is in minutes. Okay. So, what happens is that we want to this is called as Newton's law of cooling, and according to Newton's law of cooling, the heat loss. So, this is Newton's law of cooling, which states that the heat loss of a body which is minus dq dt, the minus sign represents that there is a loss. So, this heat loss is directly proportional to the delta T or the temperature difference of the body and its surrounding. Okay. So, this is the law. So, one can write it as minus dq dt equal to some k delta T, where k is some constant. And let us now talk about a body of mass m. So, this substance say has mass m and specific heat C. So, mass m and specific heat C. So, specific heat capacity say C. So, this body is at temperature T2, temperature of the body means the liquid or the substance that you are talking about, temperature T2, and say the T1 is the temperature of the surrounding. So, temperature of the body is T2. T2 and temperature of surrounding is T1. So, if the temperature falls by a small amount dt2 in a certain time interval dt, that is small t. So, this body is this substance is here, what we have referred to is of the substance here or the material, and which has the mass m, specific capacity C, and the temperature is at T2, which says 40 degree centigrade after being heated, and the temperature of the surrounding is a room temperature, which is T1, which is 27 degree centigrade. And now, this is left to cool, which means that no more heat is applied. So, according to Newton's law of cooling, we know that the heat current or the rate of change of heat is proportional to the temperature difference between the body and the surrounding. Now, let us understand that in a certain time interval small dt, in time interval small dt, I mean small dt means what I mean is this. In time interval dt, the temperature of the body falls by dt2, because T2 is the temperature of the body. So, it falls by dt2, and so then the heat that is involved here is equal to mc dt2. And so, if I divide by the time, the small time interval, so this is equal to mc dt2 by t, and which is equal to dq dt, Now, according to the law of cooling, dq dt equal to, so this is equal to minus k minus k and T2 minus T1, and so I need to solve this. I need to solve this in order to get a relationship which tells me that how as a function of time the temperature of the substance that is there falls, and which finally would come to equilibrium, thermal equilibrium if you wait for long enough, and to validate this curve, that is delta T versus the time curve. So, in order to solve that, let us solve this equation, which now looks like a minus m c dt 2 dt, which is equal to k T 2 minus T 1. So, a dt 2 divided by T 2 minus T 1 equal to a minus k over m c dt, which let us call it as a minus k, capital K dt. This capital K is another constant. This is small k. So, we can write it as in order to sort of eliminate any confusion, let us write it as k 1 dt, where k 1 equal to k over m c. And this equation can be simply integrated, and one will get a log base E T 2 minus T 1 equal to minus k 1 t plus some constant of integration, and that will be T 2 when we take this log to the other side, or take I mean exponentiate it, it becomes T 1 plus some c exponential minus k 1 t, where this c prime is nothing but equal to exponential c. Okay. So, this is the temperature, this is the way the temperature falls as a function of time, which is an exponential decay, which is seen in this particular case. Okay. So, with this we stop here on discussing thermal properties of matter, and just a very quick recapitulation of what we have done. We have talked about heat being a function of is a form of energy, and we have talked about temperature, concept of temperature, and we have talked about different temperature scales such as Celsius and Fahrenheit, and then we have also introduced the Kelvin scale of temperature, which underscores or emphasizes the concept of absolute zero, below which nothing can be cooled. And then we have talked about specific heat, the concept of specific heat for solids, liquids and gases, and then how to calculate specific heat. We have also talked about thermal expansion of solids, liquids and gases, and then we have talked about change of state, how matters change from one state to another, and the concept of latent heat therein, which is very important, because the latent heat is a form of heat which is the system accepts it in order to change while changing its state from one form to another, and it is accompanied with no change in temperature. And then we have talked about transfer of heat from one body to another, or transfer of heat from a body to its surrounding, which essentially can be done in three ways, which are convection, conduction and radiation. Especially the radiation part is important, because radiation requires no material medium to propagate, and it is actually sort of mediated by electromagnetic waves.